Okay, as we've seen, when we have an infinite series, we're actually not going to necessarily be able to add it up and find the value for it if it does converge. Geometric series turn out to be one of the few cases where we can actually find the sum of a series. So instead, when we're faced with an infinite series, we're really just going to ask whether it converges or diverges. So because of that, we want to develop a bunch of different tests. So yeah, we want to develop a series of convergence tests. Series, pun not intended. So let me use a different word, a collection of convergence tests that we can apply to any infinite series and try to determine, hopefully at least one of the tests will apply. Sort of like when you're doing integration techniques, how you want to look at an integral, and sometimes you use U substitution, sometimes you use integration by parts, et cetera, et cetera. And we want to do the same thing. We want to look at an infinite series and say, okay, let's use a certain test, and that'll tell us whether it converges or diverges, depending on the form. So we're going to develop this series of convergence tests. And what I'll say is that there is a test you want to do almost immediately. So, and that's called, I call that the test for divergence. Not all textbooks give it its own name, but it's sort of fundamental and something you should check out immediately as soon as you see an infinite series. So, so let's just look at an example. What if I gave you the sum n equals 1 to infinity of 3n minus 1 over 10n plus 1? Okay, so this is some example I made up. If you want, you can start writing out terms, right? You plug in 1, I think the numerator is 2 and the denominator is 11. You plug in 2, 5 over 21. You can compute a few of these yourself. Hopefully I'm doing it right. 8 over 31. Actually, we talked about arithmetic progressions, and both the numerator and denominator here are arithmetic progressions. Okay, and so you see these terms, sort of interesting. But you might look at this, and again, you sort of maybe have no idea at first what's happening. But let's think about plugging in like a large values of n. So, for example, if we plugged in n equals just 1,000, I mean, that's not, n equals 1,000 is not very large in some senses, but then what is the, what's the 1,000th term? So this is, let me just put some, this is the n equals first term, n equals second term, n equals 3, n equals fourth term. So I'm asking about the 1,000th term of the sum. What do you get? You'll get 29.99, because it's 3,000 minus 1, right? Over 10,001. But that's about 3,000 over 10,000, which is 3/10. And if we plug in a million, put my commas here or I'll lose it. Oops, I think I was trying to put that in the numerator. Oh, geez Louise. I was trying to put that in the numerator. Okay. Well, we get 3 million minus 1, which is 2999999 over 10 million plus 1, 10, 0, 0, 0, 0, 0, 1. The commas go there. But again, that's about 3 million. In fact, it's even closer to 3 million over 10 million, which is 3/10. And it's that thing where we talked about this a little bit, compare some improper integrals, other things, that this minus 1 and this plus 1, these are we said they're negligible as n gets large. Right, so in fact, for large n, And I'll give a little bit more of a formal argument in a moment, but for large n, 3n minus 1 over 10n plus 1 is really approximately 3n over 10n, which is 3/10. But now let's think about doing this sum and what's going to happen when we start, if we go further down the list of the sum and keep adding, right? Then the sum of this series that we started with, just copying it down again, it's about, well, it starts off with, well, so it's approximately, so let's just say, okay, the first few terms are not that close to 3/10. 5/21 is close to a quarter. But we go down the list and we just basically are adding 3/10 again. I use sort of the approximation sign here. Let me draw it a little. I'm not saying it's exactly 3/10, but it's approximately 3/10. These terms are all the same, but I'm saying once you get further down the list, I'm just going to replace all the terms with 3/10. And then that means that we're adding 3/10 over and over again. And here's the thing, because of that, this is just going to grow and grow and grow, right? I'm just adding the same number over and over again, no matter, and I'm never stopping. I'm adding a non-zero number over and over again, a fixed non-zero number. And I'm never stopping, so that we're just going to be adding, we can just keep making this bigger and bigger. If I add 10 of these kind of terms together, it's going to be bigger than 3. If I add 1,000,000 of these terms together, it's going to be bigger than 300,000, something like that. If I add 10 billion of these terms together, it's going to be bigger than 3 billion. So we can just make this as bigger and bigger and bigger. So this keeps growing. It keeps growing at the same rate forever. And therefore, this series diverges. Series diverges. Okay, and so that's the point here. The point is that when we have a series, we have the sum, but then we have the individual terms of the series, right? So what we have is we have, the terms of the series. Let me just write this kind of in general. It's, we call them A1, A2. So that's more like the sequence of the terms of the series. But then we have the series itself, which is the sum, right? And what I'm trying to say is that in general, is that if the terms of the series are not going to 0, so if the terms of the series don't go to 0, so if the terms of the series do not go to 0, then the series must diverge, because you're just adding the same non-zero number over and over again. Let me be a little more precise about this. What do we mean when the terms of the series don't go to 0? Well, that's a limit, right? It's really the limit as n goes to infinity of a sub n. So what I want to say is that if the limit as n goes to infinity of a sub n is not equal to 0, then the sum from 1 to infinity a sub n diverges. Right, so that's what's called the test for divergence. This right here is the test for divergence. This is the more formal way to say it. But if you look at the example up above, we had these terms and they weren't going to 0, they were going to 3/10. And therefore, we're adding 3/10 over and over again as we go farther down the series, and it's going to keep growing forever, so it has to diverge. So what this is saying is the very first thing you should do whenever you see an infinite series is check if the terms are going to 0. Because if the terms are not going to 0, you can immediately say it diverges. right? So maybe I'll even write this in words. Thus, the only hope a series has for converging is if its individual terms go to 0. If not, we're done. And so that's the first thing. This is the first thing you should check anytime you see an infinite series, because you might just be done. You might be able to say instantly, oh, this diverges, the terms aren't going to 0. Just as one more example of this, example I mentioned in the earlier videos, another nice example is something like this, where it's, let's see, I think I started n equals 0 to infinity, the sum of -1 to the nth power, which is 1 plus -1 plus 1 plus -1 plus 1 plus -1, etc. And here you can see it again. Now, this is a different type. It's not that, think about what happens to the terms of the series. They just bounce back and forth between -1 and 1. So here the limit as n goes to infinity of -1 to the n does not exist, right? It's bouncing back and forth between two values forever. So the series diverges. And we've seen that already, that if you look at the partial sums, you get 1, 0, 1, 0, 1, 0. So the partial sums are also bouncing back and forth, but it just fits this test. So I think it's a nice example. That's a little different because it's not that the terms are going to a specific number. It's that the limit just doesn't even exist. So this series also diverges. As a last comment, we have to be a little careful though, because now the tendency is to think if the terms go to 0, then the series converges. And that is not correct. That's actually called the converse. If in terms of logic, it's the logical converse. It's when you sort of switch the statements in the if and the then. Like here's the if part of the statement, here's the then. Or if you negate them both, maybe. You can either flip them, swap them, or negate them both. And so if I negate them both, that would say if the limit as n goes to infinity of a sub n equals 0, then the series converges. That's the converse statement. But I really want to put like a question mark here. Is this true? And the answer is no, this is false. So be careful. Don't think every series converges. Don't think that the only thing you have to do is check if the individual terms go to 0. Because we saw an example in the previous video, a harmonic series. The example that sort of shows this is false, and this is why the harmonic series is such a critical example, is a sub n equals 1 over n. The harmonic series. Sum of 1 over n equals 1 to infinity. This diverges. We proved this in two different ways. But the terms do go to 0. So the limit as n goes to infinity of 1 over n does equal 0, but the sum diverges. Sometimes when we're lazy, we just drop the thing above and below the summation sign, but I'll go ahead and write them in. And so this is a crucial example that you should keep in your head. It's not enough. The test for divergence, this is just a classic thing students do. As soon as they see the test for divergence, that becomes the only test in their head. And we're going to see these other tests. We've already given some explanations for why this example diverges. But still, if the terms don't go to 0, you're good. You're golden. You know the series diverges. Okay. All right.